Hi everyone, this is Manas, your friend and tutor, and guys, in today's session we are going to take a look at the analysis of a continuous beam and more so how to find the bending moments at different cross sections and how to apply the Clapeyrons three moment equations. Students usually find this very difficult to apply. बिल्कुल टेंशन लेने की बात नहीं है, सब चीज बड़ी बारीकी से मैं आज आपको समझाऊंगा. Don't worry. And this over here, by the way, is a continuous beam. So point number one with respect to a continuous beam is, here we go. It's a beam having more than two supports. It's quite obvious. साफ साफ दिखाई दे रहा है. दो support कौन से हैं? Support at A, then there is support at C, isn't it? And apart from those two end supports, एक और support है. There is one more support. What is that? That is the intermediate support B. So if there is a beam having end supports and apart from that it is also having some intermediate supports, then that beam falls in the category of a continuous beam. So here is the definition. If a beam has more than two supports, then that is a continuous beam. Not to worry. Okay. Point number two, and here we go. Okay. This point number two is regarding the intermediate support. Intermediate support. Well, just take a look. A over there, extreme right, that is point C. Intermediate support is point B. Point number two says that always you are going to get a negative value of the bending moment on the intermediate support. Okay, what that essentially means, let me try to demonstrate that. So let me split up the beam into two parts. So this over here is the first part, okay, and this right here is the second part. Let us try to understand this in depth. If you watch over here, this A, B, B, C. Second point, what second point is trying to convey is bending moment is going to be negative. Negative means it's going to be a clear-cut case of hogging. So if I can just show you how the beam will bend, how the nature of this bending moment is going to be, it's going to be something like this. Take a look. If it is hogging case, then it's going to bend the beam in this form. Okay, that is concavity upwards. Concavity upwards, and here also the bending moment will act in this manner. Okay, action reaction, simple, Newton's third law. So the bending moment, the nature of the bending moment will be such that it will try to bend the beam in this form. This is a hogging case. It's a negative bending moment. That's it. Point number three. What does this convey? So if the ends are simply supported, by that I mean to say at A and at C, they are simply supported. Then the bending moments over there, that means when you apply the three moment theorem, bending moment at A is going to be equal to 0, and at the same time bending moment at C is also going to be equal to 0. So this is exactly what this third point is trying to convey. Okay. Point number 4. So you can clearly see end A and end C. What are they? They are simply supported, isn't it? So you remove the simply support, you have a fixed support over there, then in that case bending moment is not going to be equal to 0. So always remember, bending moment will not be 0 if the end points are fixed, whereas the bending moment are going to be 0 when the end points are simply supported. Okay. So these 4 points in a nutshell have actually encapsulated the entire essence of this continuous beam. Now let us take up an example. Not just an example, this is more of an illustration to show you how this Clapeyrons three moment equation can essentially be applied and what are the different parameters which you first need to calculate. Right? And once you do that, you can easily apply this Clapeyrons three moment equation. Now first of all, let me tell you, you should know the concept of shear force and bending moments. If you don't know how to find the shear force at any point of the beam, if you don't know how to find the bending moment at any cross section of the beam, then things are going to get very difficult for you. And if you guys have not watched or seen my videos on shear forces and bending moments, go ahead, watch those videos, come back to this video, then everything will be crystal clear or transparent like water. Anyway, let's proceed. Here we go. Let's start. So what is Clapeyrons three moment equation? Obviously it's an equation which is going to have three distinct bending moments, isn't it? So let's have a beam first and then we'll be trying to analyze them. Okay, things are going to get very interesting, so you guys need to pay full attention. बहुत ध्यान से देखें, अच्छे से बारीकी से सब चीज़ों को समझे. मेरा चश्मा कहाँ गया? चश्मा, आंखें एकदम जल रही हैं, सोना कम हुआ है, कोई दिक्कत नहीं, पढ़ाना तो हमारा पैशन है, हमेशा पढ़ाएंगे, ठीक है? ओके, तो यार एक काम करते हैं, लेट अस ट्राई टू draw a beam. Let me make a beam, something like this. Where can I draw it? Right here at the center. किधर draw करें, इधर draw करते हैं, चलो, somewhere here. So this is a beam. This rather is a continuous beam, and you'll get to see that, don't worry. This is a continuous beam. If it's a continuous beam, then it is going to obviously have end support, और साथ में और क्या रहेगा? There is also going to be an intermediate support. तो जैसा हम लोगों ने नामकरण किया था, same form. This is going to be A. This obviously is point B, intermediate point. That's point C. Okay. Now let's say, guys, that for a certain portion of the beam, let's say this much portion of the beam, towards the right of B, we have a uniformly distributed load. Let me just show you. Let's say we have a uniformly distributed load, the magnitude of which is a W Newton per meter. That means for a distance or for a span of 1 meter, the total load acting in the downward direction will be equal to W Newtons, simply. Okay, and over here, let me apply another load. What is that load? Let's say this is load P, simply load P. Now, how do you write the Clapeyrons three-moment equation? Now, there are actually two different ways in which you can actually apply this, and especially for civil engineers who are going to come across a varying cross-section of beams and who are going to come across what do you say that? I mean, some portion of the beam will be made up of steel, some portion will be made up of aluminium. Okay, sort of a combination. In that case also, the flexural rigidity will be different. I think I have confused you guys. Don't worry. I'll explain each and everything. For now, just remember, as far as Clapeyrons three-moment equation is concerned, it's written something like this. You have got two beams. Let's say you've got two beams. This is first half of the beam, beam 1, and this is second half of the beam. Okay, so you can essentially say that this continuous beam is a combination of two simply supported beams, that is AB and BC. Once again, you can say that this continuous beam is a combination of two simply supported beams, right? Now, as far as Clapeyrons three-moment equation is concerned, it's written something like this. It's going to be MA L1. Now, some of you guys might be thinking, what the hell is L1? Let me just tell you, this is L1, yeah. And this over here is L2. Okay, MA-L1 to MB L1 plus L2 plus M at C L2 plus 6 times of A1 X1 over L1 plus 6 times of A2 L2, not L2 but X2 over L2, and all of this is going to be equal to 0. So this is the Clapeyrons three-moment equation. Now some of you guys might be thinking, okay, you know what MA is. Now if you see, this is the support at the end, and this is simply supported, and here also this is simply supported. At the ends, you are going to put this value MA and MC is equal to 0, no problem. Okay, so you are left with other terms. You are left with L1 and L2. So these things will be given to you, L1 and L2. But what about this? What about A1? What about X1? What about A2? What about X2? And what are they really? And from where you can actually calculate all those values. To know more, keep watching. Okay, so what we'll try to do is, in order to implement this equation successfully, you first need to split up the beam. So let's split it up. And when you split it up, it's going to look something of this sort. So let's have beam 1. So that's beam 1 for you. Okay, beam 1, done. And what's the name? What is the name? The name is A and that's P. Okay, similarly you are going to have over here, let me just draw this, the remaining half, right half of the beam, that is B, should be using a black color, B and that C. If you watch, there is a point load between A and B, so let me just put it up. There is a point load, okay. Right here there is a point load. And over here we have a UDL. That is W Newton per meter. Anyway, just take a look. Now, let's say we want to make the bending moment diagram. Okay, treat these two beams separately as if they have been simply supported at A and B and also B and C. You know very well that this value will work out as negative. It's a clear-cut case of Hawking bending moment. This is something which we saw in point number 2 of the previous slide. Okay, so here we go. If you try to make the bending moment of this particular case, you know very well this distance is A and this distance is B. Okay, let us try to work out everything in variables. If that is so, then the reaction over here is going to be PB over A. Reaction at A will be PB over A, and the reaction at B will be PA over PB over A, not PB over A exactly, but PB over L1. Let's say this, by the way, is L1, done, and this is going to be PA over L1. So this is going to be your reaction at the end supports. Now you can easily use this summation of all the forces in y direction is equal to 0. You can also use this summation of all the forces about a specific point, let's say point A is equal to 0. Simple equations of statics to reach these two conclusions. It's very easy, fairly easy. Okay, I'm not going to get into that aspect. This is something which I have already taught in depth in shear forces and bending moment, and I expect all of you to do this calculation on your own. Let me tell you what the bending moment is and what is the maximum value and where are you going to get that. So let me just extend this. Okay, so it's something like this. 0 level, the bending moment will be maximum where the point load is acting here, right here. So if you watch carefully, this is the way forward. That's it. Okay, that's it. This is the bending moment diagram. And if somebody asks me that, sir, what is the height of this triangle? Well, this is nothing but, let's say if you want to find the bending moment over here at this point, let me make this figure again. Very simple, very simple. You want the bending moment at point. Can you name this point? Let's say this is T, bending moment at T is equal to what? This is the reaction, how much? P A over L1, isn't it? We have a reaction here also, that is P B over L1. You want bending moment at T, you need to know what this distance is. This is A and this distance is P. It's going to be very simple. If you want moment at this point, you can consider the right portion of the beam. If you want moment at this point, same point, you can consider the left portion also. Not an issue. It's very simple. So if you do this, force multiplied by distance, this is going to work out as PA upon L1, that is the force multiplied by B. Or you can take this force also. This is going to be PB over L1 multiplied by this distance A. Whatever you do, you can either take the right hand portion of T or to the left of T. Right? From both of the cases, you are going to get the same answer. That is PAB by L1. Okay. So let me just put things into perspective. Now, let me clarify your first doubt. Your first doubt is going to be, what is this A1? So this right over here is your beam 1. This right here is beam 1. And this is beam 2. So beam 1 and beam 2, when they are combined, you have a continuous beam. It's that simple. Okay. Now, if you watch this area, if you watch area of this bending moment diagram, where shall I write this? Area of 1 Let me just write this properly. A1 is nothing but area of beam 1's BMD. And how much is that area? That is going to be equal to half of base. Base is how much? That is going to be L1 multiplied by height. Height is, you know very well, this is PAB by L1. That is PAB by L1. L1 and L1 will cancel out. I mean, you're going to be putting up numerical values when we'll be taking up examples. That is going to happen in the next video. Don't worry for now. Try to understand things. Okay, how this essentially can be applied. So on that basis, this is going to work out as PAB upon 2 simply. So this is how A1 can be calculated. Now my objective is to let you know how this X1 can be worked out. Let me have a bigger figure. Okay. Let me have a bigger figure over here. Slightly bigger one. So we've got something like this case. Right. Okay. Now the centroid is going to be somewhere here. Just remember what is X1 and what is X2. Everything will get crystal clear. Don't worry. So I'll write two things over here from two different perspectives. This is XL, distance of centroid from the left, and this over here is XR, distance of centroid from the right. What is happening? Okay. Once again, XL is distance of centroid, that is G from left, and this is distance of centroid from the right. So what is XL? XL, remember guys, is going to be equal to A plus L over 3. So instead of L, I should put up L1 over here, and XR is equal to B plus L over 3. Okay, but when you talk about beam 1, you will also have to put the value of X1. So X1 is nothing but the distance of centroid of beam 1's of beam 1 BMD from left. Once again, this X1 over here in the Clapeyrons 3-moment equation is nothing but the distance of centroid of beam 1 of beam 1's bending moment diagram from the left. That's it. Okay, so that X1, by the way, is your XL. Things clarified, right? Okay, now let us move forward towards its uniformly distributed load. Don't worry, this is also fairly simple. So if you just try to work out, this distance is nothing but L2, isn't it? This is L2 simply. You can work out the reactions. So I'm absolutely not interested in working out the reactions. Rather, I'm very much interested in making the bending moment diagram. If you watch carefully, the bending moment diagram would be something of this sort. Okay, and the highest value of bending moment will be right at the center, and this is nothing. Let me just write this. This is WL square over 8, right? Remember this. Remember this also, for a point load it is going to be equal to PAB upon L1. PAB upon L1, and as far as a uniformly distributed load is concerned, remember this formula, WL square by 8. All of these formulas can be derived by using simple concepts of shear forces and bending moments, or taking the section at different points on the beam, and you can work it out fairly easy. Okay, if we just, now these two things are over. A1, we know what A1 is, we know what X1 is. Now let's try to work out what this A2 is. So if you watch, this is A1, this is going to be A2. So this A2, just remember this formula, something which you need to by heart. A2 is going to be equal to, that is area of the parabola, more so area of parabola. Remember this formula. This is always going to be equal to 2 by 3 times the area of rectangle. Rectangle. If you watch carefully, this can be assumed to be inside a rectangle. This parabola can be assumed to be inside of a rectangle, something like this. So area of, let's say this is L, let's say this is B. So this is going to be equal to 2 by 3 times of L into B. Simply, this is the way which in which you need to calculate the area. And as far as x2 is concerned, x2, so let me just clarify. If this is the centroid, obviously the centroid is going to be somewhere here along this radius, isn't it? So this is going to be XL, this is going to be XR. So in case of x2, this is XR. Okay, x2 is distance of centroid from right in bending moment diagram. So guys, that was all for today. I'll see you in the next lecture with an example on continuous beam, and a UDL will be acting throughout the entire span. All of that and much more coming up in the next session. Until then, take care, have a nice day, keep learning, keep watching, and thank you.